Okay, in this lecture video, we're going to talk about some of the unique properties of water. So it turns out that water can function as an acid or a base, and how it functions kind of depends on what else it's interacting with. If we look at the Lewis structure of water, we can see then that just from its structure, it has acidic and basic properties because we have two acidic protons. So we know that the definition of an acid is something that donates H pluses when put in water. So this has two opportunities for that. And then we also have this oxygen atom, which can function as a proton acceptor, which makes water a base as well. So we can take a look at that with some chemical reactions to show water acting as an acid or a base. So let's take a look at water functioning as an acid first. And in this example, then, it would have to be reacting with a base. And the base that we're going to use is ammonia. So NH3 plus H2O. So again, here's our acid. Sorry, that's our base. So here's our base, here's our acid. So when those react, the acid will transfer a proton from its molecule onto the base, which gives us NH4 with a positive charge because we've added a proton. And then our acid, once it loses its proton, all that's left is an OH minus, so a hydroxide. And we call these conjugate acid-base pairs. So we have one acid-base pair here, where water is the acid and the conjugate base is the hydroxide. And then we have another conjugate acid-base pair here, where ammonia is the base and ammonium is the conjugate acid. And we'll work on that more in the in-class activity. So let's take another example then and look at where water is functioning as a base. And in this case then, that base will have to react with an acid, and the acid we'll use is hydrochloric acid. So there's our acid, and water will be our base. So now we're going to move the proton from the acid to the base, so it will go in this direction. And when that happens, we've now got our hydronium ion, H3O+, and then we've got what's left of our acid after it lost its proton, which in this case would just be the chloride ion. So again, we've got conjugate acid-base pairs. So here's our acid and its conjugate base. And then here's our base and its conjugate acid. Okay, and again, we're going to practice that in class. So water, first of all, can function as an acid. Water can also ionize because of its acid-base properties. So we look at that a couple of different ways. We could write it as water in the liquid form. When it ionizes, it breaks apart into protons or hydrogen cations that are dissolved in the water, and hydroxide anions, which are dissolved in the water. So we've broken that water molecule apart into its corresponding H plus and OH minus. We can also write that as a chemical reaction between two water molecules, where one water molecule is functioning as the acid and one water molecule is functioning as a base. So if we look at it this way, where we're going to transfer a proton from this water molecule over to this one, so that would make this molecule the base and this water molecule the acid. Then we would have H3O plus and hydroxide ion. So that's just a better way to write it, because really we don't have H pluses floating around in solution by themselves. They're always attached to a water molecule to form this hydronium. So it turns out that the amount of ionization that we have is constant. So the amount, oops, I don't want to write in red. So the amount of ionization, so how much water breaks apart into H plus and OH minuses, the amount of ionization is constant. Okay, so there's a certain number of water molecules that break apart and the rest stay whole. That value, or the amount of ionization that takes place, is described by a number that we call the ionization constant. And sometimes we refer to that as the ionization product. Symbolically, we represent it with a big K with the subscript of W. So that's the ionization product, or the ionization constant. That number is defined as the product then of the concentration of the hydronium ion, so how much H3O plus is floating around, times the concentration of the hydroxide ion. And since this number is constant, it doesn't ever change, that value is always equal to 1.0 times 10 to the minus 14th. And that's measured at 25 degrees Celsius. So this number will change if we change the temperature, but we're usually talking about room temperature. So note that we don't have any units on this number, and that's because if we had units, they would be weird, so we just leave them off. What's important to note, though, is that the units of concentration here for the hydronium and the hydroxide, those units must always be in molarity. Okay, so concentrations, when plugged into the ionization product, are always in molarity. And when you multiply those concentrations, the molarity of the hydronium ion times the molarity of the hydroxide ion, you will always get 1.0 times 10 to the minus 14th when you're at 25 degrees Celsius. So this means that we can solve for different values, and we can take a look at the relative amounts of the hydronium and the hydroxide concentrations. So since the ionization product is always constant, if we have a special case where the concentration of the hydronium ion is equal to the concentration of the hydroxide ion, then each of those concentrations would be 1.0 times 10 to the minus 7 molar. And if you have equal amounts of hydronium and equal amount as you do hydroxide, then we say that that solution is neutral. Okay? If instead you have more hydronium ions floating around than you have hydroxide ions, then that would be an acidic solution. So you have an acid, so you have a whole bunch of H pluses that have been donated, so that's an acidic solution. Whereas if you have a whole bunch of hydroxides compared to the amount of hydronium that you have floating around, we now have a basic solution. Because remember, a base's job is to produce hydroxide ion when you put it in water. So let's take a look at an example to use that. So let's say we know that the concentration of hydronium ion, so the amount of H pluses, right, that have been released by an acid, is 4.5 times 10 to the minus 7 molar. Okay, so we want to know then, what is the concentration of hydroxide ions? Well, since the Kw is constant, the hydronium ion concentration times the hydroxide ion concentration, we can solve for the hydroxide ion concentration. It would be the Kw value divided by the hydronium ion concentration. which in this case then would be the Kw, which is 1.0 times 10 to the minus 14th, divided by 4.5 times 10 to the minus 7. And again, I'm leaving my units off because we know that everything is in molarity here. And if I divide that, I get 2.2 times 10 to the minus 8th molar. So then we can compare the amount of hydronium ion with the amount of hydroxide ion. So there was 4.5 times 10 to the minus 7 molar hydronium ion, and that value is larger than 2.2 times 10 to the minus 8th molar for the hydroxide ion. So since we have a greater concentration of hydronium ion than we do of hydroxide ion, we can say then that milk is acidic. Who would have thought? So that's an example of the different types of calculations you can do with the ionization product and then looking at relative concentrations of hydronium and hydroxide ion in a solution.